Okay, here's section 9.6, and this is the last one that actually deals with learning a new test. And after this, obviously, you're going to have your test over sections 9.1 through 9.6. So we have two tests today, and they're both pretty easy tests. They're nice ones to end with, I would say. The first one is called our ratio test. And we have let our series a sub n be a series with non-zero terms, and the series of a sub n will converge absolutely if the limit as n approaches infinity, you have the absolute value of a sub n plus 1, so basically your next term, divided by a sub n if that is less than 1. So whenever this ratio is the limit of this ratio, if it's less than 1, it's going to converge. Well, then it's going to diverge if this limit is greater than 1. So it's absolute value, which is really nice. It's the next term. Instead of dividing, I will end up multiplying by the reciprocal. And obviously here, if it's greater than 1, then it diverges. The ratio test is inconclusive if this limit equals 1. Meaning inconclusive that you have to then use a different test. So limit n's approaching infinity, and we have a sub n plus 1, our next term, divided by our previous term or multiplied by the reciprocal. If it equals 1, it is inconclusive. Ratio test is most useful for series that converge rapidly. So whenever you have series involving factorial or exponentials, this is a really nice test that we can use for it. Looking at a couple examples, in this situation, again, it looks close to being geometric, but unfortunately you have this other n here, so that's not going to be geometric. And then let's test it using our ratio test. I don't know why I'm writing ratio test with it, but there it is. And we have our limit. N is approaching infinity. It's absolute value, which we don't need in this situation because it's always going to be positive. We need our next term. So in place of n, it's n plus 1. And then remember, our next term would be n, this would be n plus 1 as well. So 3 to the power of n plus 1, instead of writing it like that, we're going to write it as 3 to the power of n times 3, divided by, instead of 2 to the power of n plus 1, 2 to the power of n times 2. So that's our next term, that a sub n plus 1. And instead of dividing and creating a compound fraction, instead we're just going to multiply by the reciprocal right away. And the reciprocal would be 2 to the power of n in the numerator. And in the denominator, I would have n times 3 to the power of n. Obviously, simplify. So 3 to the power of n simplifies out. 2 to the power of n simplifies out. And now I have the limit. N is approaching infinity. In the numerator, we have 3 times n plus 1. And the denominator, we have 2 times n. Well, I know that this limit is equal to 3 halves. Great, 3 halves is greater than 1. Therefore, because it's greater than 1, going back up, we know that it diverges. So therefore, diverges. A pretty simple, easy test to use. Again, this is used for series involving factorials or exponentials. That makes it really nice. So our next example, when we have factorials, it's really convenient for it. One thing to take note of when you have this 2 times n factorial, you basically, it's n plus 1 and then this portion of it, so because that's in parentheses to start, then it would be factorial. So when you're looking for that n plus 1, you have to specifically put it just with the n. And in this situation, because we have parentheses, it's 2 times n in parentheses and then factorial. In parentheses, it needs to be 2 times the n plus 1 and then factorial, creating this to be 2n plus 2 factorial. Well, if I expand this, 2n plus 2 factorial becomes, it's 2n plus 2, but instead of subtracting 1, we know that our previous term was just 2n. So instead of going down by 1, because technically it has to be always in parentheses n minus 1, if you distribute that, you're actually always going to go down by 2 each term. So then the next term, obviously, here would be 2n minus 2, and then we'd have times 2n minus 4, and this would continue, so I'm going to put the factorial at the end there. So that's one thing that you have to be very conscious of, is that it's specifically n plus 1 to start, and then you distribute the 2, creating 2n plus 2, and then that's factorial. But your previous term is no longer, I'm just going to subtract 1. You're subtracting 1 from the n. So make note of that situation when you're dealing with your ratio test. So with the ratio test, I need my limit, n's approaching infinity, absolute value. Well, I need my a sub n plus 1. So in this situation, we already wrote out what 2 times our n plus 1 factorial will create. And it does create 2n plus 2 factorial, but I know I want things to simplify out, so I'm going to put it as 2n plus 2 times 2n, and then I'm going to put factorial because I know when I multiply by the reciprocal, things will then simplify out. This is divided by n plus 1 to the power of 5. Multiply by the reciprocal of the original, so n to the 5th, divided by 2n factorial. 2n factorials end up simplifying out. Now I have the limit, n is approaching infinity. I have n to the 5th times 2n plus 5 divided by n plus 1 to the 5th. I know the degree of the numerator is greater than the degree of the denominator, so you could apply L'Hopital 5 times, but that would be rather annoying. And so as long as the degree of the numerator is greater than the degree of the denominator, this limit is equal to infinity. Well, infinity obviously is greater than 1, and therefore this series is going to diverge as well. So as a note, you might want to put in here, if whenever the degree of the numerator is greater than the degree of the denominator, the limit will equal infinity. And that's, of course, if your limit is approaching infinity. So limit, I'm going to put n is approaching infinity, will equal infinity. And obviously then that's going to be greater than 1, so it's going to diverge. A couple more kind of weird examples with our good old ratio test. Again, we see factorials, so factorials are kind of a hint to use your ratio test with this. And keep in mind, remember that this is n plus 1, and then it's a factorial, and that's kind of weird that we're going to square this thing too. And then in the denominator, it's 3 times n plus 1, and that's in parentheses, and then factorial, just like the previous problem. So for our ratio test, limit n's approaching infinity, our next term is going to be n plus 1. I'm expanding, figuring out what this thing is. Actually, I'll need another set of parentheses because then it has to be squared. Well, this one, my coefficient in front is a 1, so if I have n plus 1 factorial, my next term is going to be n factorial. And that entire thing is squared. So that's kind of goofy. This is divided by, remember now this becomes 3n plus 3. Instead of putting factorial here, this is times. It's not 3n plus 2, but it's just 3n, and then that's factorial. Multiply by the reciprocal of the original, 3n factorial, divided by n factorial squared. Obviously the 3n factorial simplify out. Here it says a kind of a strange situation because we have a factorial squared, which doesn't really happen too often. It's pretty rare even. But if you have properties of exponents, you have this n plus 1 times n factorial. Because you're multiplying, you can distribute that squared to both terms. So I'm just going to write that out, what this looks like. And it's basically, here's the property that you're using. If you have a times b squared, you know that that's a squared times b squared. So in this situation, this will give us n plus 1 squared times n factorial squared. So I'm distributing the squared to both parts there. Divided by 3n plus 3, And oops, then I also have in there n factorial squared. Those things simplify out, leaving us with the limit n is approaching infinity, and we have n plus 1, that quantity squared, divided by 3n plus 3. Again, in this situation, the degree of the numerator is greater than the degree of the denominator. You could apply L'Hopital's rule here, but there's no need to. We know that once this happens, this limit is going to equal infinity. We know infinity is greater than 1. Therefore, this series will diverge. So, a pretty easy test to use with our ratio test. Just some weird things that happen, especially when you have factorial and you're adding for your next term. If you have that coefficient, make sure that you understand that this means 3n plus 3 times 3n and then factorial, but you'd have to consistently change by 3 as you go through there. And one other kind of weird one here, number 32. Again, this is just what this notation means. Obviously, well, negative 1 to the power of n is going to be alternating, but this notation, it means that the first term is 2. The second term is 2 times 4. The third term is 2 times 4 times 6. The fourth term, obviously, 2 times 4 times 6 times 8, and that continues. So that's what they mean by this notation. When we apply a ratio test, then it's a limit n's approaching infinity. It's absolute value, so you can ignore the negative 1 to the power of n. But to write in your next term, you have to keep the 2 times 4 times 6 dot 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 times 2n. Now my next term would mean I need 2n, and then it would be plus 2. Because again, keep in mind it's n plus 1, so when you distribute the 2, that's going to create a 2n plus 2. That's divided by 2 times 5 times 8 dot 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 times 3n minus 1. If I made this n plus 1, that would end up making it 3n plus 2. So this notation, keep in mind, like your third term is 2 times 4 times 6 in the numerator. In the denominator, it's 2 times 5 times 8. So then you have to keep all of these previous terms, because our formula says a sub n plus 1. So our next term, it's all of these terms multiplied together. Multiply by the reciprocal. So 2 times 5 times 8 dot 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 times 3n minus 1. The denominator would become 2 times 4 times 6 dot 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 times 2n. And obviously now things simplify out really, really nicely. So the 246 times 2n, 246 times 2n, those simplify out. 258, blah, 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 3n minus 1. 2 times 5 times 8, blah, 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 3 times n minus 1. Those all simplify out, and we're left now with the limit. N is approaching infinity, and we have 2n plus 2 divided by 3n plus 2. Well, our degrees are the same, so look at our leading coefficients. This is equal to 2/3. That limit is less than 1. Therefore, it will converge. So just a couple of different things what that n plus 1 means. I think your notes here, there are some really good examples that you can reference back to if you have any issues with it. Then we also have what's called our root test. And our root test we're going to use, basically, we're going to create an nth root. So we'll use this especially when we have anything to the power of n. That's when this is going to be really helpful. So a similar situation here is that we're going to figure out when our series will converge and when it will diverge. So if you have this series and we have a sub n, it will converge absolutely, and we don't have to really be concerned about the absolutely portion like we do when we have our alternating series. But it's a limit n's approaching infinity, and you have the square root, or I'm sorry, the nth root of the absolute value of a sub n. It will converge again if this is less than 1. So just like your ratio test, it diverges if this limit, as n is approaches infinity, if you take the nth root of the absolute value of a sub n if it's greater than 1. And the test is inconclusive. We're just writing this a lot so that you remember what the test is. limit n's approaching infinity, the nth root of the absolute value of a sub n, inconclusive if it equals 1. So exact same scenario that you have with your ratio test. Looking at some examples, they're very obvious when you should be using your the root test. So here it's like you have something raised to the power of n. Number 42, it's raised to the power of 3n, which is just fine. 48, that ugly thing is raised to the power of n. So that's kind of the hint, like, hey, use the root test here to get rid of that exponent, and that's pretty nice to use. So here's our series, and then all it is limit n's approaching infinity, and it's the nth root. It is the absolute value. It doesn't matter in this situation. So it's 2n divided by n plus 1. That's to the power of n. Well, really convenient. This is going to become the limit n's approaching infinity, 2n divided by n plus 1. Once I simplify, the degree of the numerator and denominator are the same. Go to our leading coefficients. This is equal to 2, which is greater than 1. Therefore, diverges. So pretty easy scenario here. 42. There is a negative in this one, but again, as soon as you see everything raised to that power of n or 3n, that's basically screaming root test. So our limit n's approaching infinity. Even though it's to the power of 3n, we want the nth root every time. It is absolute value, and so I guess you could start with putting in the negative 2n, but in the long run, because it's absolute value, it's not gonna, that negative we can get rid of. We have 3n plus 1 in the denominator, all to the power of 3n. Well, this limit as n approaches infinity, I know that I would end up dividing that exponent by n. It is absolute value. Well, I'm going to make it positive and just call it 2n divided by 3n plus 1. That's all to the power of 3. You don't have to go through and distribute. You know that in this situation, obviously that's going to make it 2n cubed. This denominator is going to be cubed, and therefore you don't have to expand everything. But the degree of the numerator and denominator are the same. Therefore, this limit will equal 2/3. That's less than 1, and it will converge. And the last one, kind of an ugly looking thing, but still it's raised to the power of n. So you look at it, we have our limit, n is approaching infinity. The nth root, I don't need absolute value here. If you want to put it in, it's never going to hurt. Natural log n divided by n to the power of n. When we simplify, limit n is approaching infinity, and we have natural log n divided by n. For this particular situation, when you do plug things in, yes, it gives you infinity divided by infinity. You do have to use L'Hopital's rule. Good thing we have a fraction. This is our limit, n is approaching infinity. Derivative of the numerator is 1 divided by n. Derivative of the denominator is 1. Plug things in. We get 1 divided by infinity, which is equal to 0. 0 is less than 1. Therefore, this series will also converge. So the ratio test and root test, really easy to use. Root test is whenever you have something to the power of n or 3n or 5n or whatever it may be. Your ratio test is really helpful whenever you have exponentials or when you have a factorial. So that's kind of that's all of our tests that we have, sections 2 through 6. I will have a sheet here for you that has all of the tests on it, which is kind of nice. It has a table that has basically what has to happen, so you can see different situations or which ones you can find the sum for, and I'll show you that in a second here. But guidelines for testing a series for convergence or divergence. First of all, does the nth term approach 0? And if it doesn't, it will always diverge, and basically then you're using your nth term test. So really basic tests that we learned in the first section, or section 2. Then look, is it a specific type of a test? Is it geometric, which is obvious to tell? P-series, which is obvious to tell. Telescoping, which is pretty obvious to tell, and alternating. So we want to look for those because those are the easiest. Next, can you apply your integral test? You have to be able to integrate. The root test, that's basically you have to have it to the power of n. And the ratio test, yeah, if you have that factorial or if you have exponential. So kind of go in the, like, this is the easiest, these are the next easiest, they're getting tougher. And then, annoyingly, if those things don't work, you can use direct comparison or limit comparison. So that's kind of the process that you can go through. This next section here, go through on your own and try to figure out what is the easiest way to prove convergence or divergence of each series. And so quickly go through and solve those 7 problems, I guess. And write down what test that you used, if it converges or diverges. Let's make it easy. Go through and just write down what test you would use. And if you want to show a little bit of work for it, that would be good. You don't have to show too much. So take about 5 minutes here to do that. Okay, if you went through and just kind of wrote down what you would have now, or what you would do with each test, or each series, sorry. First one is pretty obvious that it's nth term, and those are great when you can look at it and say, yep, we know that that limit equals to 1/3. That obviously doesn't equal 0. We know then it will diverge. So as long as you can look at it and say, well, I know that what this limit is, that's an easy problem to do. This one, a little bit disguised geometric, but obviously pi is a number, and it's raised to the power of n. So geometric, pi over 6, that's less than 1, so it's going to converge. C is a little bit ugly. Basically, to set this up, an integral test, I know that usually when you use your ratio test or your root test, you want to have a fraction with it, or especially for ratio test. If I use direct or limit comparison, that's pretty ugly. It's not alternating. That's just a pretty ugly problem. But we can use our integral test if we have this situation. Then we can say, well, our u value will be negative x squared. Differential of u is going to be negative 2x differential of x. Great, plug in a negative 2, take out a negative 1/2. And then you're left with e to the power of u differential of u, which pretty easy to integrate from there. So, kind of an ugly looking one. Integral test sometimes I think is kind of hard to recognize because you have to be able to integrate it. And yeah, they're sometimes difficult. For D, looking at this one, you have a lot of options. You could try direct comparison. You can try limit comparison, works for a lot of things. You can use your integral test. If we look at this and just set up our direct comparison, we know if we have 1 divided by 3n plus 1, because you're adding 1, that's going to make that denominator bigger, meaning the fraction will be smaller. That's less than 1 divided by 3n. Well, if I look at this situation, it'd be my p series I'm comparing it to, and the power is 1. So remember, if your power is equal to 1, it diverges. If our bigger diverges, can we say anything about the smaller one? No, because smaller numbers could possibly converge. So direct comparison didn't work for this situation. You could use limit comparison, and that b sub n I would use would be 1 divided by 3 times n. So you can definitely use that. Remember, limit comparison, you have to show the limit with it. You could also use your integral test for that because you can definitely integrate that with natural log. E is awesome. You can use alternating series, so that negative 1 to the power of n or negative 1 to the power of n plus 1 is really nice to see. Alternating series, make sure you show the 2 conditions. Number 1, limit n's approaching infinity, 3 divided by 4n plus 1, that's equal to 0. Good, that condition is met. Are your terms decreasing? Well, yeah, you'd have n plus 1 plus 1. It's going to get smaller. Terms are decreasing. That would converge. F, this is an ugly situation when you have like that factorial and exponential. That's your ratio test, but looking at our problems that we did today, ratio test is pretty darn easy to use. So our next term would be n plus 1 factorial, which we'd write it out this way, divided by 10 to the nth plus 1, so we're going to write it out this way, multiply by the reciprocal of what we started with, 10 to the nth n factorial, simplifies out. In this situation, I'd have n plus 1 divided by 10. Obviously that's going to equal infinity, therefore that one, it's greater than 1, it will diverge. And then the last one, it's all raised to the power of n, that's your root test. That one would end up converging. The limit would equal 1/2, so pretty easy. Looking at the table on page 644, I have a handout for you that has that table on there with all the different types of series that I was talking about earlier. It's nice, it just has everything together and what's happening, and so that's a good place. It's a nice thing to have. And that's the last section now before you have your test for section 6, or sections 1 through 6. And the test is only out of 80 points. So that's kind of nice because you have the 2 tests. So this first half, 1 through 6, is out of 80. The second half, I think, is out of 60 to 70, somewhere in there. So 2 a little bit smaller tests. A lot of times you're going to be given a situation where you have to figure out, I'm going to say, here's 5, 6, 7 different series. You have to use each test one time. You can use them more than once. You know, going through and, okay, what can I use, especially like direct comparison for, because that's really specific. What can I use my integral test for? What one can be a ratio test? What one can be the root test? So going through and just figuring out which one is which. And that's it. Have a great day.